Now, what happens if we set up a pulse sequence which doesn't have a spin echo? So we have our slice selective RF pulse. We have our phase encoding gradient. And then at some point over here we have TE. And we know we need our frequency encoding gradient. Now, as we already discussed, in the absence of that 180-degree RF pulse, right, we know there's going to be a rephasing lobe for our slice select gradient. We know that the orientation of the initial application of this frequency encoding gradient has to be the opposite polarity to the frequency encoding gradient that we use to sample the signal. And I've set this up so that the magnitude and duration of this initial application of the frequency encoding gradient, what is sometimes called the dephasing lobe, matches the first half of the frequency encoding gradient under which we sample the signal. This point, of course, being TE. This gradient will dephase the spins. This first half will rephase the spins. So that, again, if we look at what happens to the signal, and only looking at what's happening to the signal, the component of what's happening as a result of this gradient magnetic field. So yes, T2 star relaxation, that's all going on. I'm just going to ignore that for a minute. We have no change when this gradient is off. A loss of signal due to dephasing when we turn it on. When we turn it off again, it's having no effect. And at this point, we recover back to the same level that we were before. And if it stays on, it trails off again. So this is called a gradient echo, or a gradient recalled echo. And this is a gradient echo pulse sequence. The only thing there really is to know about the difference between a gradient echo and a spin echo pulse sequence is that the gradient echo pulse sequence does not have a 180-degree RF pulse. And as a fine point, just one second, the polarity of these dephasing and rephasing lobes of the frequency encoding gradient are different because of the absence of that 180-degree RF pulse. Go ahead.
Where are you encoding the frequency information?
Same place, right here. While we sample the signal, this gradient magnetic field has to be on. Because at the time that we sample the signal, we want our spins, depending on where they are along the frequency encoding direction, to have different frequencies of precession. It's no different than the spin echo pulse sequence. Yes?
Is the angle the same of the RF as the spin echo, 90 degrees?
The flip angle. So we're going to talk about that next. Okay? At this point, yes, it is. Absolutely. It's 90 degrees. I haven't changed any of that. We'll talk about why you might not do that in just a minute. But so is everyone clear that a gradient echo pulse sequence is just a spin echo pulse sequence where you leave out the 180-degree RF pulse? Okay? Now, if we ask someone who knows a little bit about MR, about what would be the characteristics of a gradient echo pulse sequence. So hopefully they'll know that there is no 180-degree RF pulse, like we just said. That's sort of the main salient difference. Another thing they might know is that since we don't have that 180-degree RF pulse, we don't have this issue where we have to wait for the spins to dephase, and then after the 180, we have to wait for them to rephase again. The dephasing and rephasing that occurs due to these gradient magnetic fields is simply a function of how strong the gradients are, as well as how long you leave them on. you can make the process happen much faster simply by making your gradient much steeper. In a spin echo pulse sequence, you don't have that option. The time it takes for dephasing and rephasing is a function of the difference in precessional frequency of the spins. We have no way to change that. You have to wait that time between 90 and 180 and then 180 and TE. In the gradient echo pulse sequence, we could compress this and make it dramatically shorter simply by changing the amplitude of the gradient magnetic fields. So another sort of salient difference to be aware of is that a gradient echo pulse sequence is potentially much faster. And the original approaches to fast imaging in MR were using gradient echo pulse sequences, where that's exactly what was done. Everything was compressed so we could get from the initial RF pulse to sampling the signal within a very short period of time. Right? As a result, with gradient echo pulse sequences, we are ready to repeat things very quickly, which means that within a given TR, you could potentially include many more excite many more slices. Or, as we'll talk about in just a minute, we might actually be able to just image with a much shorter TR overall. Okay. The other thing that someone who knows a little bit about MR will probably tell you is that they can always spot a gradient echo image based on the parameters by looking at the flip angle, which is sometimes we use the symbol alpha, meaning how many degrees is the magnetization tip. Now, everything we've talked about until this morning has assumed that we turn on our RF and we rotate the magnetization 90 degrees. And that's generally true, but it's not universally true. And there might be potential benefits to using a flip angle that is not equal to 90 degrees. This is definitely associated with gradient echo pulse sequences, but it's a misconception that somehow it's a unique feature of gradient echo imaging. And so I want to address this whole issue of how do we choose the angle to which we will flip the magnetization, and we'll talk about it in the context of gradient echo pulse sequences, but keep in mind that it's not really something that's unique to gradient echo at all. So the way I would conceptualize it is when we take the longitudinal magnetization and we knock it into the transverse plane and then turn off the RF once we're at 90 degrees and wait and watch what's happening. So what happens? We have loss of transverse magnetization due to dephasing, and at the same time there is regrowth of longitudinal Did I say there's loss of transverse magnetization and regrowth of longitudinal magnetization. The transverse magnetization loss happens much more rapidly than longitudinal magnetization recovers. If we wait a really long time, like we said at the beginning of the week, 3 to 5 times T1, we will fully recover all of the longitudinal magnetization we started out with. Which means that if we now repeat this again, in other words, if our TR is very long, every time we repeat our RF pulse, if we wait a long enough time, we will have that same large amount of transverse magnetization. What happens if the TR is shorter? Well, when the TR gets shorter, we knock it down the first time, so we're at rest, right? The patient goes in the scanner, they're laying there with their longitudinal magnetization. We tip it down to 90 degrees, and we now watch what happens. So it starts to recover, and if our TR becomes shorter, before it gets back to where it started, we knock it down again. And now we have less transverse magnetization because there was less longitudinal magnetization recovered to turn into transverse magnetization. And it will start to recover, and when we get to that same TR, it won't even get back to where it got the second time around. After 3 to 4 iterations, we get into what we call a steady state, where the magnetization on each successive TR will recover to the same point. And each time we will generate the same amount of transverse magnetization corresponding to that degree of recovery of longitudinal magnetization that occurs on each iteration of the TR. And this is what we call the steady state signal. Now, as you can imagine, there are two factors which will govern what this steady state signal is going to be. Any idea what those would be? For a given situation, why would we have a smaller steady state signal or a larger steady state signal?
When achieving that curve.
So it depends on that, but what parameters or what characteristics? So TR is one of them. Again, we already said that if the TR is very long, right, then we can allow this to fully recover before each successive iteration and get that same large amount of signal. What else could govern this? Such as the T1, exactly. So if the T1 is very short, right, that means we knock this down and it recovers right away. So even if the TR is relatively short, because it recovers so quickly, we always will have a full recovery of our longitudinal magnetization, and our steady state signal will be large. If the T1 is longer, on the other hand, right, if it's a very slow process, then even if the TR is very long, we won't make it all the way back, and we will end up in a lower steady state. Now, it turns out that, on the other hand, let's say we have a situation where our TR is very long. Okay? TR is very long, T1 is very short, so we're in this steady state where we recover all of our magnetization on each successive TR. Well, by changing the amount of RF power that I apply to the patient, instead of flipping this 90 degrees, I could, let's say, only flip it down 45 degrees. That's simply a matter of either cutting the B1 power in half or applying the same strength for half the amount of time. If I put this down to 45 degrees, I've now created less signal than if I put it all the way down to 90 degrees. Right? Once I put it down to 45 degrees, and now, as we wait and watch this recover, if we wait a really long time, TR, we will fully recover all of that longitudinal magnetization and generate the same amount of transverse magnetization at 45 degrees that we did the first time. Right? We'll be in that same steady state. What if we shorten the TR? Right? If we shorten the TR, well, we won't make it quite all the way back. And when we knock the amount of recovered longitudinal magnetization down to 45 degrees, we will have a little bit less, and we can, with that shorter TR, we will be in a shorter steady state. Now, it turns out that if the TR is extremely long, in which situation will we have a higher steady state magnetization? When we rotate our magnetization 45 degrees, or when we rotate it 90 degrees? If the TR is extremely long, meaning we allow this to recover all the way after every TR. 45 will have a larger amount of transverse magnetization?
No, less.
Will have less, exactly. So my question was, which one will have a larger steady state signal? Right? So 90 degrees, when the TR is long, will give us a greater amount of steady state signal. What happens if the TR is very short? Well, if the TR is extremely short, when we knock this down to 90 degrees, in a short TR, it doesn't recover very much longitudinal magnetization, meaning on our second iteration, it doesn't generate that much signal, and even less on the third. And we get into a steady state where we have very little longitudinal magnetization recovered after each TR and very little steady state signal created. Okay? What happens if we take that same situation with the short TR and only knock this down 45 degrees. Well, the first time around, we don't get as much signal as we would have at 90 degrees. But this is largely almost all the way recovered. So in that short TR, it's going to recover to a higher degree of longitudinal magnetization than it did when we knocked it down to 90 and only waited for that short TR. So with this 45 degree flip and the short TR, the steady state signal will actually be larger than with the 90 degree flip angle. So whereas we initially thought that rotating the magnetization to 90 degrees is always going to give us the most signal, right? That's still true if we're only doing it once. But as soon as we start repeating this multiple times, the rate at which you repeat it, and or, by the way, the rate at which it recovers, will influence which angle of rotation will give us the greatest steady state signal. Right? And it turns out that what we can do is we can graph signal intensity versus this angle. Right? We can go from 0 to 90. Right? There's no question that going beyond 90 doesn't really give us any additional advantage. Right? Once we go beyond 90, we have less net transverse magnetization. So if we think of a situation where the TR is extremely long or the T1 is extremely short, the maximum steady state, right, signal intensity is going to be achieved at a large, meaning 90 degree, flip angle. And obviously, if the flip angle is 0, we're not going to generate any signal. And we can actually, by experiment, determine a curve which shows us the relative steady state signal intensity achieved by each of these various angles. Now, if we make the TR shorter, or if the T1 of the tissue happens to be very short, as we've just said, a lesser flip angle may give us a greater degree of steady state signal intensity. So this curve might change, right, and look something like this, where it peaks, you know, maybe at 40 degrees. Each of these is unique for some combination of T1 and TR. Right? As soon as one of those parameters changes, the flip angle that's going to give us the greatest steady state signal is also going to change. Now, this angle, which gives us the maximal signal, is called the Ernst angle. Right. So in responding to that question, well, when we do gradient echo imaging, isn't the flip angle going to be different? Well, at least one of the reasons why we might choose a specific flip angle at this point has to do with maximizing steady state signal. And since the T1 of the tissue is not something that we can control, it is what it is, that decision would be based on the TR that we're going to use to image. And in fact, we can compute, right, based on a certain TR, what would be the optimal flip angle. Unless the TR is extremely long, 90 degrees is not going to be optimal. Right? So some people might be surprised to know that even when we do, right, spin echo imaging, where we think of that always being a 90 degree flip, the TRs are generally not that long, not long enough to allow full recovery of the longitudinal magnetization. And as a result, typically these are going to be accomplished with flip angles that are less than 90 degrees. Maybe 70. It'll all depend on the situation and the TR. And the scanners are often optimized to choose the flip angle based on the other parameters, specifically TR, that you select. So this is how choosing the flip angle and specifically identifying the Ernst angle can allow you to maximize signal in the image. There's another way that we can use this flip angle, however. Question? No? Okay. Question?
Yes. When you talk about the T1 of that tissue, how can you talk about that in a given slice? You're going to have vastly different tissues than T1s.
Okay, and different tissues technically will have different Ernst angles. That's life. So you're right. There's nothing you can do about that. But within tissue, there's some range of T1, and we can do our best to choose an angle that is going to be optimal as a whole for whatever it is that you're imaging. But you're absolutely right. So for example, let's say you're doing musculoskeletal imaging where you have lots of fat and lots of muscle. So the T1 of fat and muscle are quite different. The Ernst angle for fat and muscle will be different. Now, in that case, we might make a choice and say, well, the T1 of fat is very short, so generally its steady state signal is always going to be higher anyway. So maybe we'll choose our Ernst angle based on tissue. So the fat water thing, that's kind of an extreme in terms of differences in T1. In general, gradations of T1, for example, between gray matter and white matter in the brain, they're not so enormous. But it's a good point. It's an observation. There's nothing we can do about it. That's the way it is. Yes.
So with something that is CSF that is not green-white, that has much longer T1, right? If you're gonna have frequent TRs at short intervals, will you not see signal from CSF at all because you're not allowing T1 for CSF to sort of reach T1?
Okay. So it's, first of all, to not see any signal at all, you would have to have an extremely short TR, and then you would also be, you would be suppressing other signal as well. The other thing you have to realize is it becomes more complex because CSF, for example, also has a much higher proton density. So even though its steady state signal might be suppressed due to this very rapid repetition of TR, it's also starting out with a lot more signal at the outset. So it's not such a simple relationship. And in practice, no, when you use a short TR, you don't all of a sudden have no signal from CSF. Okay. So one way that we can choose the flip angle would be to maximize signal. So I want to point out one other option for why we might choose one flip angle over another. Let's make an assumption that we're imaging with a relatively short TR. Okay. So if we're imaging with a relatively short TR, we forget about this whole flip angle thing for a minute and just go back to Monday when we talked about T1 contrast and how shortening the TR is going to bring out differences in our signal that reflect the fact that spins recovered their longitudinal magnetization at different rates, had a different T1. Does that sound familiar? Vaguely familiar, maybe? Okay. When we give our 90-degree RF pulse, if we have two tissues, and they have the same proton density, just to make things simple, we generate some signal. If our TR is really long, even though they have a different T1, they recover their longitudinal magnetization at different rates. If we wait long enough, well, they look the same. Therefore, when we generate the signal, they look the same. There is no contrast that's a function of T1. Their T1s are different, but we don't see it because we wait so long. If, on the other hand, we shorten our TR, so we generate this signal, and before they fully recover, we knock them down again, all of a sudden our signal has a contrast embedded in it. The two different tissues have different amounts of signal. That's a function of how much they recovered their longitudinal magnetization. We only see that difference when we use a short TR. Okay? Now, if we use a 90-degree RF pulse, we are going to be taking all of that difference based on a differential recovery of longitudinal magnetization and immediately turning it into a difference in transverse magnetization, a difference in signal. Okay? What happens, on the other hand, if after they are in the transverse plane with our short TR, instead of putting them all the way down to 90 degrees, we take these and we knock them down only part way, let's say 45 degrees. Well, now all of a sudden, whatever that difference was in terms of how much longitudinal magnetization had been recovered, only part of it is changed into signal amplitude. Not only that, but on our next iteration, right, during our next TR, as these recover, they are much closer together and have a lot less distance left to recover. So when we watch what happens during TR, there isn't going to be as much separation of the longitudinal magnetization of these spins. In a sense, by using this narrower flip angle, we are suppressing the differences that show up in the signal related to the fact that the two tissues have the same T1, have different T1. They have different T1s, but it's only when we knock them down all the way and they have this long way to recover that when they relax at different rates, we can see a large difference which gets turned into signal. Otherwise, if we only knock them down part of the way, they're already half the way home. There isn't going to be that much time for them to differentiate during that recovery of longitudinal magnetization. And as a result, there's a smaller difference which we turn into signal with our narrower flip angle. So by using a larger flip angle, we essentially bring out these differences based on different T1 relaxation times. Whereas with a narrow flip angle, there's only a little bit of difference between these spins based on their T1 relaxation time, which we then turn into signal. So it turns out that, now first of all, this will only work, will only have this effect if we're imaging with a short TR. Because if you're imaging with a really long TR, everything fully recovers and there's no T1 contrast anyway. So we can, in a sense, think of the fact that we have a short TR image which should have a lot of T1 contrast. But if we make the flip angle narrow, we are suppressing the T1 contrast that would otherwise be in the image. And this is very commonly used in the setting of gradient echo imaging. Because in gradient echo images, we discussed the fact that things, because we don't have that 180-degree pulse, we can compress this down and do all of this very rapidly. When we get to the end of TE, right, well, waiting until TR serves what function? Making our TR longer, or like, why don't we just go back right to the beginning and start over again? Okay, one issue is signal, but even if we wait, why would we wait a longer or shorter period of time? What are we doing by adjusting the TR, the point at which we go back to the beginning and start this again? Right. Our TR is adjusting our T1 contrast in the image. Well, now all of a sudden we have another way to modulate that T1 contrast in the image. The only reason we need to lengthen the TR is if for some reason we want to suppress this T1 contrast in the image. But now all of a sudden, if our TR is short, we have the option of modulating the flip angle to suppress that T1 contrast. And in fact, as our T1 gets shorter and shorter and shorter, this Ernst angle curve shifts to the left, such that the optimal angle, this should have gone all the way to 90, in terms of signal to noise, becomes narrower and narrower and narrower. So these two things really synergize together, that when we image at a shorter TR in our gradient echo pulse sequence, right, we, in essence, need to make our flip angle narrower to preserve signal, but at the same time, we're able to use that to modulate T1 contrast in the image. And generally, whereas it seemed on Monday like the way that we modulate T1 contrast is by adjusting the TR, and the way we modulate T2 contrast is by adjusting the TE, in gradient echo imaging, TR is sort of not a factor. Right? T1 contrast is modulated much more, and I'll show you this right now, modulated by the flip angle. And it's gradient echo, there's no 180-degree RF pulse, so strictly speaking it's not T2, but it's T2 star contrast, right, is still modulated by the TE. So let's just look at this for a minute. Okay, so these are gradient echo images where we've changed the TR, right, all the way from 20 milliseconds to 1 second. And as I think it was Victoria said, that one of the issues as we shorten the TR is that what do you notice sort of overall? Yeah, much less signal, because we are in a much lower steady state. If you don't allow it to recover, right, little longitudinal magnetization means little signal. So using an extremely short TR is problematic because it gives you much lower signal to noise. Now, if you look at the contrast in these images, look, for example, at the contrast between CSF and brain. Well, I mean, the CSF is pretty much always dark here. And by the time we get to the sort of really longest TR, we can see a little bit of a change in the gray-white contrast. But there isn't this sort of dramatic change in contrast with the TR. But on the other hand, if we look at the TE, and these images we actually looked at once already, you can see that by adjusting your TE, right, from 5 to 125 milliseconds, or even over a shorter range, that you completely invert the contrast in the images. This is that situation that we talked about on Monday, right, where we have our, let's do this with a different color. And right, different proton densities, relaxing at different rates. So depending on where you are, whether your TE is over here versus over here, blue and green are going to have a complete opposite arrangement of their signal amplitude. The overall signal, by the way, is always going to be lower the longer you wait for TE. Okay? And then finally, right, so this is a series of gradient echo images where everything stays the same except for the flip angle. So in this case, the TR is 500 milliseconds. In spin echo imaging, at least, that would be a short TR, typically what we would use for T1 weighted images. Yet, if we change, and the TE is also short here, right? The TE in this case is 10 milliseconds. But if we narrow the flip angle sufficiently, we can completely suppress that T1 contrast that otherwise would be in the image if we used a much larger flip angle. Is this clear why this happens? Right? When we knock those spins down, it has to do with how much room they have to recover their longitudinal magnetization and differentiate themselves, so to speak, based on their different T1. Because that difference in longitudinal magnetization when we give the next RF pulse is what is going to determine whether we see contrast based on longitudinal relaxation, that is based on T1 in the image. One other thing here, if you look at these images, which are all shown at the same window and level setting, what's the Ernst angle? Anyone? How could you tell from looking at this?
55
Okay, why do you say 55?
minus the signal to noise.
Right, so the Ernst angle, we're essentially replicating that graph which I drew. Right? This is the flip angle. This is signal intensity. So we have a whole bunch of different flip angles, and we can plot the signal intensity where it peaks is the Ernst angle. So you would typically do this by measuring, but we could sort of approximate that it seems to be somewhere in the 45, 55 range that the image seems to have the largest amount of signal. Okay? Any questions about this?
Isn't it the Ernst angle dependent on tissue? So couldn't you have two Ernst angles here
Absolutely.
for different sections?
Sure, depending on where you measure. And if you're measuring in two different places, you won't necessarily identify the same angle because it's a function of TR and T1. In all of these measurements, the TR is the same, but the T1, of course, varies based on tissue. Okay? I mean, I think you see that most obviously if you look at CSF, which has a much longer T1.